So welcome back. In this video, we will continue to discuss the hidden Markov models. Before we move on to another topic that's going to be the Viterbi algorithm, let's illustrate what we haven't seen so far with one example about the robot localization. So we have discussed the forward algorithm, and the forward algorithm is an algorithm to estimate what is the beliefs of the current state given all the past evidence. So in this example here, we're going to use one robot like this. So it is the inspiration for this example is a mobile robot that we have a sensor that can measure the distance from the robot to the nearest obstacles that we have. So and this sensor can measure the distance for different angles. So we're going to simplify this and say that the sensor can measure if we have one obstacle nearby in 4 different directions. So it's going to be like this: north, south, east, and west. And we also have a mobile robot, so you're going to move around the map, but when we have a robot like this, the surface can be a little bit slippery, so we command, but we are not sure if the robot actually was able to process that command to move to a new state. We're going to simplify the problem, thinking that we have a map like this, and this map has discrete positions. So we can think that we have like the position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like this, and we can number of them. So we can think that we have a representation for this map is like a large state space where we have all these states. So we have the state 1, 2, 3 until the final state here. And we have initial probabilities for those states, and we can think that these initial probabilities are if we don't know about where the robot is or where is it more likely to be located, we can say that it's going to be a uniform distribution. So we assign the same distribution, the same probabilities for all states. And we have these 2 models here. That's a sensor model and motion model. These are simplifications for a real robot. So in the sensor model, we can read in each directions there is a wall, but never more than one mistake. So this is a noisy sensor. It can make just one mistake or no mistakes at all. I cannot do 2 or more mistakes. And you have the motion model, that is the robot may not execute the action with a small probability. So if you say move to the left or move to the right, it may, for instance, stay in the same position with a small probability because, you know, it touched some obstacle, it could not move, or it was a little bit slippery and they stay in the same position, something like that. And we're going to revisit those models and make some more realistic assumptions when we discuss particle filtering at the end of this lecture. But for now, it is enough. So let's suppose that we want to know where the robot is, so which state the robot is. So basically what I'm saying is that I'm going to start with a uniform distribution, so all equal probabilities at the beginning, but I want to track those probabilities, and I hope that I can find one position that is more likely than the others. That would be our inference for where the robot is located right now. And if we think about this, we are discussing the forward algorithm for the hidden Markov model. So what I'm saying that the states are not directly observable, right? So these guys here, we cannot observe it directly. What we can observe is the results of the distance sensor. And this distance sensor is a little bit noisy, so it will not be perfect. At the same time, we have the transition probabilities going to tell us how we update those probabilities from the time t to the time t plus 1. And well, these transition probabilities will not be perfect as well, because we have this motion model that says that we can move to the next position or not. we can stay in the same position with a small probability. So this is the idea. And we're going to use the colors to indicate the probabilities. So we have this information here, and the darker colors indicate higher probabilities, lighter colors indicate smaller probabilities. So we make our first reading of the sensor. So we're going to have it our first observation. So it's going to be our first emission. And in this case, it's being represented here by green, that we detected a wall in the top and a wall here on the bottom, but we did not find any walls in the left or in the right. So if you have this observation and we update our the probabilities of our states, what we're going to have is that, okay, some states become more likely, other states become less likely, and some states become impossible. Remember that we only, our sensors, we have this assumption that you only make at most one mistake. So in order to be here in this position, the state number 1, it would require 2 mistakes. One is about this sensor here, right? It's saying that there is no obstacle, but in this case there is this wall here. So yeah, is one mistake. The second mistake is this guy here that's saying there is a wall on the bottom, but actually there is no wall here. So in order to be in this position, it would require 2 mistakes. And okay, so this position will be impossible given our assumption of 1 mistake at a time. And this position here is likely because it matches. We have a wall on the top and bottom, but no walls on left and right. But the same applies to here, and the same applies to here, and the same applies to here, and the same applies to here, as well as because you have this symmetric map, it also applies to the row on the bottom. And this state here, they are less likely but still possible. For instance, if I have a robot here, this reading on the top here is compatible because it found a wall. This would be a mistake, but these 2 readings here are also compatible with the reading that we had. So these 2 states here would require 1 mistake in terms of the reading, so they are less likely, but it's still possible. So they are marked with this light gray. So now I ask the robot to move to the right, so it goes to this position. And actually we don't know exactly where the robot is, so keep that in mind, but we are assigning probability to all the states that we believe that are more likely according to the hidden Markov model. So the robot is now in this position. And we make another reading, and again we notice that we have walls on top and bottom, and we update our beliefs based on this reading. So for instance, this state here is less likely. It's possible because we commanded the robot to move to the right, but it may have stayed in the same position. So it could be still in this position here, but it's less likely than this. And these 3 positions that we have here, here, here on the top, and these 3 here, here, here on the bottom are the most compatible ones with the evidence that we haven't seen so far. And we continue to command the robot to move to the right and doing readings from the sensor. And as we read, and we continue seeing that we have walls on the top and bottom, we stay more and more confident that we are in this middle part of the map here. And as we continue to read, we stay more and more confident. So we see that the probabilities start to become closer to 1. And now, because of the symmetry that we have in this map, we are very confident that we are or in this position here on the top or this position here on the bottom. Okay, after a few time steps and some readings, we get to a position that we are very confident about the location of the robot. We see that because we got in this position here that eliminated the symmetry of the map, we become more confident that we are here on the top in this top position. So what happened here is that we have this reading that we detected a wall on the top, but no walls in the other three directions. And this is not compatible with this guy here, that it would require one mistake here plus another mistake here. So we are very confident that we are in this position. It's also possible that we are in this position, this position, this position, this position, this position, because the robot may have not moved correctly, so it may be still in those positions, but we are very confident that we are in the correct position of the robot. Okay, so far we have used the forward algorithm, so there is not this S here, to track the probability of the states over time. So what we have done is to compute what is the probability of x1, and as the time passes and we observe new evidence, the probability of x2, and again time passes and observe some emission probability of x3, and so on. And I'm going to switch now to a different type of query, that is one MPE query, the most probable explanation. So in this case, what we would like to know is what is the most likely assignment for all variables x1, x2, x3, and so forth, given the evidence E1, E2, E3, and so forth. So to understand this, we have seen this before a few times, but to make it a little bit more concrete, we can think about a table that's going to be very large. And this table has the joint probability of all hidden variables given, let's suppose you have just 3, just make it a little bit smaller, given all the evidence. So we have E1, E2, E3, and so on. So yeah, it can be much larger than this if we have more variables. So we have more time steps. So this will have this probability. And we have here the variables x1, x2, x3, and we also have like columns in the table, and we also have the probability, and the probability is this guy here, right? So we observed these variables, so they will not be represented here as columns because we have already observed, so going to be fixed values. It's only interesting to have in the table the variables that have different values, so they can assume different values, but the variables that have already been observed, they have a fixed one, so they are not very interesting. So we're going to track the values of x1, x2, x3, and the probabilities. So this table here, we know that's going to be exponential over the number of variables. It will depend on how many values each variable can assume, but we know that's going to be exponential n, so it's something that xpn. And so what we are interested in? So we are interested in two things. First, which of those rows has the highest probability? So there's going to be a variation of this. This is actually the max for x1 to t for all time steps, the probability of x1 to t given evidence 1 to t, right? So this is the maximum one. So basically it's looking here and seeing what is the maximum value. So let's suppose that is this guy here. And the second thing that we are interested in is actually what is the assignment that gives this maximum probability. That's going to be the values for x1, x2, x3. So when I know which values I should put here, so I will have the highest probability possible considering all possible assignments. So yeah, that is the problem. We can understand this problem sort of a classification problem, but with the difference that when we discussed the classification using Bayes nets, we were interested in just one class variable. Now we have one class variable per each time step. So we're going to have some sort of a multi-variable classification. Okay, we can use this state trellis, that is a graph, in order to better understand the state transitions over time. So we have here in this graph all the variables, so x1, x2, and so far until xn, and we have the possible values that these variables can assume. In this case, it's going to be sun and rain. And we have those arcs here, the edges, pointing in all those directions between two time steps, and it basically means the possible transitions that we can have. Those arcs, they have this weight here. And it is basically the change in the probability values as I make one transition in time and one observation of evidence. So just to be a little bit more clear here, we can think about this edge here, right? So what does it mean? It's going to be the transition from sun to sun plus one observation of evidence. So it's going to be the transition, so it's going to be I reaching sun from sun, and multiplying by the probability of the evidence that I don't know what it is, so I will just call it E2 given sun. And for this edge here, what we have the probability of sun given that it came from rain times the probability of the evidence E2 given that I am now at the sun position. And for the forward algorithm, what we do, we sum these two things together and we get the probability of x2. You may say that we don't know this because we first sum these guys here and later on we multiply by those guys here, so that is how we wrote the algorithm. But yeah, it's the same thing actually, because if you think about it, this term here, the evidence, is going to be a constant because we're going to sum over xt minus 1. So considering xt minus 1, this guy here is a constant, so we actually move it here, but that is just for computational reasons to make the algorithm less expensive. But we can understand that the computation is done as it is specified here in this state trellis graph. Okay, so what's going to happen here at the end is that the forward algorithm will compute the sum of path probabilities that end in the same state, such as xn equals sun. So we're going to continue doing this, and we can understand that at the end, when we sum the probabilities of coming from here and the guys coming from here, we will get this guy, the probability of xn equals sun. So it's basically what the forward algorithm is computing. If we use that same idea of computing the entire table, we haven't used this idea before. This table will have the probability of x1, x2 till xn given e1, e2 till en, so all the evidence that we have observed. So basically what we are doing is for the forward algorithm, we have all the variables here until xn, and we have the probabilities here. And while we have this huge table that, okay, we'll never compute that because it's going to be exponential in size. But at the end, what we are doing, we are looking at everywhere that we have sum here for xn. We are going to do the summation of all these probabilities here, and this is going to be this guy. And for all the rain entries here, we're going to sum all those probabilities, and it's going to be the probability of rain. So basically what is going on with the forward algorithm. So I'm going to do something different, and what's going to compute this different thing is what we call the Viterbi algorithm. I am not interested in these sums that lead to xn equal different possible values, but I want to compute the path with the highest probability. So we can think that now we have all those weights equal to this expression here in the arcs, and I have all possible combinations here of variables sum and range, values sum and range for all possible variables. So I'm going to think that we have sum for all possible variables, and I'm going to do the summation, the addition between all these arcs here for this path. We can think that, no, I'm going to have a different path now. I'm going to be sum, just one range, and back to sum, and sum for all remaining values. So you needed to sum this arc here, and do the summation with this, and sum with this, and do this. So we have all the possible paths, and I'm interested in the one that has the highest probability. And although the forward and the Viterb algorithm, they sound like very different, in the end they are very similar to each other. And we can compare both here. And the main difference is the fact that in the forward algorithm, I'm doing the summations to eliminate the variables in a certain order. And for the Viterb algorithm, I'm going to do a very similar thing, that is eliminate the variables, but using a max operation. And to understand this a little better, and we will return to this topic when we have a specific lecture about MPE and map queries. But just let's think a little bit about a very simple graph. And I think that thinking about very simple things is a good idea in order to try to understand some concepts. Let's suppose that we have just a Markov chain with x1, x2, and x3, just to make it very simple. And we want to compute the probability of x3, right? So that's going to be the forward algorithm. So what we do here, what we do is, first, we use case analysis. That is very important to us. So we introduce x1 and x2 by doing the summation. So if you do the summation for x1 and the summation for x2, and I will be able to write this as the joint probability for x1, x2, and x3. Again, you can think the other way around, that is marginalization. So when we have the joint and we sum the variables and we get the marginal. And as we come from here, we can rewrite this using the chain rule for the Bayesian network as the probability of x1 times the probability of x2 given x1 times the probability of x3 given x2. And as we do that, okay, we're going to avoid building a table as large as this. So we do the factorization, and the variable elimination algorithm tells us that we can move the summations just to the relevant terms. So, okay, in this case here, we can move the elimination of x2 to this point here, and we'll have something like this. x1, sorry about this, px1, and I'm going to move the summation for x2 here. That's going to help us to save a little bit of time and space. Okay, so that's good. That is what we saw in the variable elimination lecture. And now what we're going to do is to compute something that's different, but we can, relate it one thing to the other, but what we want to compute is the max. And let's think about the max for now, and later on let's see how we find the argmax, right? So I want the maximum probability for this table. So that's x1, x2, x3, right? So I want to find the maximum assignment, the maximum probability for this table. And what we can do, again, so it's going to be the maximum for x1, x2, x3. So we're going to find the row that has the maximum value. So what we can do is, again, to rewrite this as a max x1, x2, x3 for the chain rule on the Bayesian network. So I'm going to be x1, probability of x2 given x1, probability of x3 given x2, and that's it. And what is interesting in terms of math is that the same property that is valid for the sum is also valid for the max. So we can move the max to the positions in order to eliminate the variables sooner. So we can move, for instance, the max for x3 to here, for max for x2 to here, and keep the max for x1 in this position. So this is going to be the same as the max for x1, x1, times the max for x2, the probability of x2 given x1, times the max for x3 given the probability of x3 given x2. And we're going to save us also space and time. So basically it's the same algorithm that is variable elimination, but now I'm not eliminating the variables, but I'm computing the maximum. But we can use the same idea that we use it for variable elimination in order to compute the maximum. So that is the idea. Let's come back to the slides and let's use one example to illustrate this idea in a little bit more concrete way. So let's suppose that we have a sort of a game and we have two coins. Both are unfair. So we have a core C1 and C2. So someone flips the coin sequentially, but we don't know which one. So we have a person that has, the person selects one of the coins, we don't know which one, and flips the coin. And we observe the outcomes, there are heads or tails. We know that C1 has a higher probability of heads and C2 has a higher probability of tails. And the person has a preference to keep the same coin that he or she is going to start with, and the coin is chosen randomly with equal probabilities. So we're going to start like this. So the idea is that we start with equal probabilities. As the time passes, the person can decide to switch the coin or keep the same one, and it has a slight preference to keep the same coin than to change the coins, right? So let's suppose that we start, the person decides I'm going to change the coin or not, and it flips and shows the outcome to us. We don't know which coin is it. Again, the person decides going to change the coin or not, do the move, and flip the coin again, and we observe the outcomes and so on. And the outcomes are like this. So if you have the coin C1, it has a higher probability of heads than tails. And if you have the coin C2, it has a high probability of tails than heads. And let's see how we can compute the return algorithm with this example. Okay, so let's take a look at one numerical example to see if you have the correct understanding. So in this game here, we started with 0.5 and 0.5 probabilities. I'm going to change the color here to make it easier to read in this blue background. So let's suppose that the person takes one coin from the bag without looking at that, and take a look on the coin and decides going to change the coin or not. So it's going to first do a transition in time, and after that the person flips the coin and we see the outcome, and we continue doing. So for the transition in time, you have to do this part of the computation, and later on we multiply by the emission probabilities that we, according to the observation that we have made. So for the x2 variable, we have actually two possibilities, and I'm going to take the maximum between them. One is that we came from the same coin C1, and in this case it's going to be 0.5, that is the probability of the coin C1, times, well, we are keeping the same coin, so that is easier for us. I'm going to keep the same coin here, going to be 0.7. This is one possibility. And the other possibility is actually we started with the coin C2 and we decided to switch. So in this case, the coin C2 also have 0.5 probability times the probability of switching coin, that is going to be like this guy here, coming from C2 and going to C1, and going to be 0.3. And we want to take the maximum between these two things, and the maximum is this guy here. So we have 0.5 times 0.7, going to be 0.35. And now we need to multiply by the evidence. And we observed heads. Okay, heads is more likely for C1, so we have this row here. So I'm going to be the multiplication by 0.8. And this is going to be 0.28. All right, so 0.28 is the probability that goes here. And it's going to be good to take note of where we came from, right? So in this case, we came from here. What it means that we took this maximum here that was corresponding to staying with the coin C1. So we started with C1 and we kept C1 in the second time step. We need also to compute the probability for this blue cell here. So it's going to be the maximum between two possibilities. One that we started with C1 and it decided to switch. So I'm going to be 0.5 times 0.3. In the second one, we had C2 and decided to keep C2. We're going to be 0.5 times 0.7, right? So we see that we have symmetric probabilities here. So here is equal to this guy here, and this guy here is equal to the guy on the other side here. So we're just switching places here. So again, the maximum is going to be here, but this maximum has a different interpretation. In this case, we are saying that we are staying with C2, and it's going to be 0.35 times. Now it's different because heads is less likely for C2. When we see heads and C2 here, we're going to be just 0.2, so times 0.2, and that's going to be equal to 0.07. So 0.07 goes here. So basically what he's saying here is that if we have just one step of this game, you would say that and we have observed heads in this only in the only iteration of the game, we would say that it's more likely that the person took from the bag the coin C1, decided to keep it, and flip the coin, and we saw the head. Okay, we can do it for one more time step. So we're going to switch from here to here, and the computation is the same thing, right? So I'm going to repeat this. Again, to be here on this top cell, the yellow one, you're going to have maximum. So this is the cell for C1. And we have two possibilities. The first one, we came from the C1. So I'm going to be 0.28. That's probability of X2 equal C1. And we're going to multiply by 0.7. Yeah, that is the probability of staying in C1. Just me erase this. Otherwise, it's going to be more difficult to explain. Okay, so the probability of staying in C1 is going to be 0.7. Or the other side, it came from here that has this very small probability times the probability of switching, that is this guy here, 0.3. So, okay, yeah, the maximum is going to be this guy here for sure. And 0.28 times 0.7 is going to be 0.196. Okay, but now we had a tail at outcome. So, yeah, that is less likely for C1. So I'm going to be times 0.2, and this guy is going to be 0.0392. So here what comes is 0.0392. Okay, but again, we have the maximum from this side here. That means that we're going to continue with the coin C1 in this case. So we did not switch coins. Let me just erase here. So we have So here basically we are recording the fact that in this case here, if this is the highest probability at the end of our simulation, we're going to come back from here and come back from here, and that's going to be the sequence of steps that give us the maximum, the assignment with a maximum probability. For the other cell, what we have to do, again, is the same thing. It's the maximum. One possibility is switching coins, and the other one is keeping the same coin. So let's try to keep it the same pattern that we were doing before. So let's first look at switching coins. So it's going to be 0.28, that is the coin C1 times, I'm going to switch coins. Switching coins, I'm going from C1 to C2, so it's going to be 0.3, or the other possibility is 0.07 times keeping the same coin C2, that's going to be 0.7. And so we have these two possibilities here, and the one that has the highest probability is going to be this guy here. So the probability is 0.084, and in this case I'm saying that the highest probability is actually coming from C1. So I'm going to raise this guy here, and so I'm going to be registered that in this case we came from C1 and we decided to switch to C2, and 0.84 times it's going to be tails, and tails for C2 has a highest probability, so it's going to be 0.8, and 0.84 times 0.8 is equal to 0.0672. So what's going to record here is 0.672. So if the game stops now, what you're going to see is that, well, we have two observations, heads first, tails later. The one that has the highest probability in this case is going to be this guy here. So if you have just two iterations of the game, I would say that the highest, the assignment with highest probability is, and you have to follow those arrows here, is going to be C2 for X3. It's going to be, and we come from here, and going to be C1 for X2, and also following this arrow here, going to be C1 for X1. So yeah, that is the Viterb algorithm. We don't have much space here to continue doing that, so I'm going to switch slide. I'm going to see the final computation. So these are the numbers at the end. So we can see that if we continue doing this, we're going to have the arrows pointing and the information where we came from. And so in this case, we have these heads, tails, tails, and tails. So just to look here, the assignment with the highest probability is this one, right? And what is the assignment? The assignment is C2 in this case here, and we come back from here, and you're going to be C2 again here, and we come back from here, and going to be C2 here too, and we came from this guy that is C1, and came back to this guy that is C1. So our output for this game is going to be C1, C1, C2, C2, C2. And a few observations here is that it is a mistake, and we cannot see here in this example because it's very simple. It is a mistake to say that the output is the highest probability for each of these columns here, right? So if you say, okay, the assignment with highest probability is going to be, I don't know, here between C1 and C2 because both have 0.5. So I'm going to, I don't know, flip a coin and say that is something like, oh, it can be like C2 by chance. And I look here and took the highest one that's going to be 0.28. And I'm going to see now here is going to be C1. And we're going to look here and take the highest one. So in this case, it's going to be C2. And look here at the highest one. Then going to C2. And look here at the highest one. It's going to be C2. And this is the output for the game, and that is an incorrect answer. It is an approximation. We can show, and I'm going to come back to this later on when we discuss these MP queries, but frequently when it's too expensive to compute the true output, what people do as an approximation is to compute the maximum for each of the marginals here. So each for the maximum for each variables like we are doing here, and giving this an approximation to the MP query. But yeah, it is not going to be the same result always. It can change. I have one more complicated example later on in the slides, and I'll show that to you. Another observation is that as we look here, we can see that the probabilities are going down and down with time. So if we just erase this mess here, and that is very natural, because if you look at what we are computing here, is basically multiplication by this, even though we take the maximum, but it's the maximum after having multiplying this. So this is a number between 0 and 1, so I'm going to decrease this value, and after I take the value again multiply by a number between 0 and 1. So we have this, if you look at the numbers, 0.5, and I'm going to start to decrease 0.28, 0.0392, 0.005, and 0.002, and so on. So it tends to decrease. As we are just doing multiplications here, it's a good scenario for the log probabilities, because we're going to replace those multiplications by sums. So the standard implementation with the Viterbi algorithm is with log probabilities instead of using just probabilities. It will avoid the situation where the number is so small that the floating number representation that we have in the computers do not have enough bits to represent that number, and suddenly the number becomes 0, and we lose our computation. So we're going to replace those small numbers by larger negative numbers that are the log probabilities, and we gain the fact that we can operate with sums instead of multiplications. So this is the Viterbi algorithm. Yeah, I see an error here already. So there is an N here, not a T. So if you look at the algorithm, it's very similar to the forward algorithm, right? So basically we are doing something that's very similar in terms of computations, just replacing the sum by a max. All right, so let's just go through this. I prefer the blue color for some reason. So we're going to simulate this for n time steps. We have the transition probability, we have the emission probability, we have the prior probability of the states. So it would be better if having the prior probability, yeah, of the initial, states x1 are going to be px1 in a sequence of observations e2 to et, and I'm going to return the maximum. So here it's just an algorithm to compute the max, so going to be the max probability, but usually we are more interested into the argmax than the max, but we need to compute the max, find the correct row and give the answer, and the answer will come from the path that we have into that we had when we computed the algorithm, and we can store this path with two different techniques. One is having an additional data structure where we point to the states that we came from, and the other one very similar to what we did when we were simulating the algorithm, and the second one is to actually reverse the computations and do the computation from the end to the initial position. We're going to see both and we're going to implement both too in the tutorials. We started with this implementation that do the backtrack, so the reverse computation, but when we discuss the MPE and map queries in a specific lecture, we're going to also implement this additional data structure that keeps the assignments. So okay, the algorithm is very simple. So we keep a table that we now call M. It has the initial probabilities. We iterate for all time steps, so t from 2 to n, and we iterate for each possible state xt and xt minus 1. And yeah, basically we are checking for the maximum, right? So we're gonna do this computation here, checking if the previous state times the transition probability is going to be larger than what we have stored. So for the first iteration, because we have stored the value with 0, we're going to replace this, and we keep in doing this for every time that we find a larger multiplication like this. So at the end, we need to multiply by the emission probabilities, and we multiply here, and it do this for the entire for all the time steps. So again, the complexity of Viterb algorithm is the same as we had for the forward, and the mini forward algorithm is going to be dictated by these 3 forwards that we have here, here, and here. One that operates over n, the other one for the number of states, and another one for the number of states. So it's going to be n times the number of states times the number of states, that is n number of states squared. So this is the Viterb algorithm, but there is still one piece missing, that is how we compute the argmax. But that's going to be relatively simple, given that we have this table M here that we can use in our computation. So let's have a break now, conclude this video, and we'll continue in the next video discussing how to compute the argmax, the assignment with a maximum probability. See you soon.